Hi, today we are going to take a look at this vintage avionics unit. This thing is an indicator bearing. It was used in a Tornado aircraft. This stuff was manufactured by Marconi. There is a circular connector and a small fan here. We have, of course, a CRT. It is located inside the shield, which should be in the middle here. And we have two amplifiers. This thing uses electromagnetic deflection, of course. So we have two identical amplifiers. Okay, so we can see here a pair of power transistors. We have the driver here. And it is the same for the second axis. On that side, we have obviously the circuit for the cathode. It's a kind of amplifier probably. And here we have the power supply for the CRT. So we can see the post acceleration here. This connection is probably for the acceleration anode. And we have here 4 other wires. So we should have one for the cathode. One should be connected to that board, which seems to be the green wire here. This one. Okay, so which is this wire here? So this wire should be the cathode, so the cathode is modulated. Now we should have the filament. So probably these two wires here. Okay, so let's see with the knob meter. Bingo, so there is a resistance of 2 ohms approximately. So here we should have the heater. So the voltage for the heater is produced by this power supply. Okay, I didn't see, so it is written, so we have the beam control. So this is effectively the cathode circuit. And we have here the deflection. It is written X deflection amplifier. And here it is impossible to see, but underneath the wires here we can read probably Y deflection circuit. Okay, if the other one is X, this one is Y. There is no mystery. And we have two capacitors here. So we have 2 blue wires here. And you can see that these wires seem connected to the fan here. So this is maybe the capacitor for phase shift of this AC motor. Okay, so I think it can be interesting to make it work. It is not very complicated, but for that we need the schematic of one amplifier here. And of course the beam control. I will start by the reverse engineering of one amplifier, this one for example. I will desolder all wires here. So on this amplifier, there is an IC here. I don't know if it is an op-amp or something else from Harris. Okay, so you can see this track here. So this track is connected to this capacitor. This is a negative pole of this capacitor. Positive is here. So this seems to be the ground. So in the middle here. So this is the positive voltage, probably plus 12. And minus 12 here. So you can see that we have the negative power supply on pin 6 here. So this is not compatible with the classic op-amp, for example. So this is maybe a particular amplifier or something else. What we can do is to test if the power supplies are present on the connector here. Okay, so bingo, we have a pin. I don't know, but one pin. So probably we need to apply the power supplies here, plus 12 and minus 12. Okay, so let's see the positive rail here. Okay, it is also present on the connector. Anyway, the only power supply on that unit is a high voltage power supply. And we can see that we don't have any output for plus and minus 12. This is a schematic diagram of one deflection amplifier. There is a differential amplifier here on the left The deflection coil is here. The goal is to convert the differential input here into a current. So therefore there is these two current sense resistors in parallel. So this is the main feedback. There is an adjustment here of the gain, and there is another adjustment here of the offset. So there is a local feedback here which permits to control the voltage gain of this amplifier. There is a current limiter here. We need approximately 0.6 volt here. So therefore, because there is one voltage drop, we should have 1.2 volt here. And because we have a divider by 2, we need a voltage of approximately 2.5 volt. And because we have a resistor here of 1 ohm, the current limit is approximately 2.5 amps. We can see that we have also a nonlinear circuit. This arrangement permits to decrease the gain when the voltage is above a given limit here. So I assume that this permits to correct some nonlinearities due to the deflection coils. This is the schematic diagram of the beam control circuit. The output is here. The signal is connected to the grid of the CRT, the VNELT actually. There is here a voltage of minus 62 volts. This transistor is in common base configuration. So we can see that there is a current here flowing through this resistor, which depends on the voltage applied to this terminal here. So these two pins of the circular connector permits to change the luminosity of the CRT when this transistor is off. So this one is on. So therefore the same current flows through the emitter here and through the collector here. So therefore there is a voltage drop across this resistor. So therefore the grid here is above this voltage. Otherwise, when this transistor is on, that is to say one of these three transistors is on, there is here a voltage of minus 0.6 volts approximately. There is a voltage divider 27K and 1K6 here. So if you suppose that you have a voltage close to 0 volt here, so that means that the voltage here is minus 0.6 approximately. So therefore the emitter is at 0 volt. So therefore this transistor is off because there is a null voltage, okay, between the base and the emitter here. So therefore the grid here is at minus 62 volts. So this is a blanking circuit. If one of these transistors is on, the CRT is blank. So this is the main control of the CRT. Okay, you can see that there is a load resistance of 100 ohms here, and this signal is fed directly to this comparator LM111. So this permits to turn on or off the CRT. And we have two other controls of the beam here. So you can see that we have a voltage doubler here, Schenkel type. So we need these two inputs, enough AC voltage in order to turn off these two transistors. But actually this circuit doesn't work on my unit. There is here a very small voltage, approximately 50 to 100 millivolts. So there is maybe a failure on my unit, or maybe there is something I don't understand. Anyway, in order to activate this unit, I have disconnected these two resistors in order to turn off these two transistors here. For the test, this indicator is connected to a dual function generator. I am going to test this unit using Lissajous patterns. So here we have two sine signals, 100 Hz and 90 degrees phase shift. I am going to change the phase shift. (180 degrees). Zero. I am going to change the frequency, 100 Hz and 200 Hz, 300, 400. It is possible to modulate the signals.